Saxon Advanced Mathematics, Lesson 45. Hi students, you're going to be happy with what I have to tell you on this one, but first I have to give you my sad news. I tried to get a box of markers and have them last all through the semester, if you will, but like the chunk of time from the fall to Christmas time. And this is what I'm down to, you guys. I get a great big box of like 64 colors, and I try to match the color that I use to the color of the book because it makes it a lot easier to keep track of which videotapes go to which students, right? Because I look at the videos and sometimes it's confusing. But if I know the green marker means the green book, then I can be really sure of what your which videos belong to you. But look what I'm down to, you guys. These are my only colors. This is what I use for Algebra 1/2. I've been using the pink for Algebra 2. I've been using that brown for Algebra 1. This is blue, orange, and red. That means I have these to choose from for your marker. I've burned out all of your markers. So it's going to be catch as catch can for the rest of the year. Or the rest of 2020 anyway. So that's why I've switched to brown, and I'm sorry. You guys are like the orphans. Because my pens, I get used up the fastest with you because I write the most. The lessons are longer, and it just makes a difference. All right, so that's why I'm using brown. Conditional permutations. Here's the thing about permutations. We learned that there's a formula you can use. N things take an R at a time, and the formula looks like this, right? And you can shortcut the process. You can even do this really easy on a calculator. The problem, though, is that we oftentimes encounter permutation problems that don't fit the basic scenario. They have lots of weird conditions attached to them, and it makes it impossible for them to fit into this. So we have to go back to our drawing out each one and having to logic it separately. And so that's what we're going to do today is do some more of those problems that have special conditions attached that do not fit this lovely simple scenario. But as far as I'm concerned, they're the fun ones because you get to think each one through. Example 45.1. How many odd counting numbers can be formed from the digits 3, 4, and 5 if there is no repetition of the digits permitted? Okay, odd counting numbers is what we're trying to create. Okay, we have 3 to choose from, but it doesn't say it has to be a 3-digit number. So the first thing we can do is say, okay, what if we just use one box, right? We could have a 1-digit number, and there are 2 of these that would work in there, right? We could either put in 3 or 5. So there are 2 choices we could put into our box, and that would give us 2 different permutations. What if we tried to make a 2-digit number? Well, this digit we know has to be either 3 or 5, because if 4 is here, it's not going to be an odd number. So we could put 3 or 5, so we have 2 choices to put in that box. Now, there's no repetition allowed, so that means whichever number we put in here, we could put any of the 3 in there, but we'll have used 1 up there. So we only have 2 choices to go in here. 2 times 2 means there are 4 different permutations in that scenario. What if we have a 3-digit number? I wish I could see your faces right now, because you may be going, oh yeah, I get it, this is really simple. Or you might be going, what in the world is she talking about? I hope it's the first. Okay, so odd counting number, that means 3 or 5 are the only digits that can go here, because that's how odd numbers work, right? We can have even numbers here, but this digit is the one that has to be odd. So once again, this has to be 3 or 5. Then we have 2 choices of the 2 remaining numbers to go there, and then here we'll only have 1 remaining choice. All right, so that's how my brain figured that out. Some people say, well, wait, shouldn't it be like this? Shouldn't you say 2 here and then fill in this one next and then that one? Why are you going ones, tens, hundreds place? Shouldn't you go from the smallest to the biggest and the middle? Spoilers, it doesn't matter because look, they both give you the same answer, which is 2 times 2, which is 4, right? There's 2 times 2, there's 2 times 2. So the order doesn't matter in these. Remember, we're multiplying, and multiplication order doesn't matter. So what we do is we multiply each of the different scenarios, and then we add to say that there are 10 ways that these 3 numbers can be arranged to make an odd counting number. But we had to do some thinking, didn't we? Okay, that's the first one, and that's the right answer, P.S. Let's try another one. Find the number of odd 3-digit counting numbers. So they have to be odds, and they have to be 3-digit. I'm not going to write down counting number this time. It's just a reminder that that means we don't need to worry about fractions or decimals, which is a gift. Thank you, John. Okay, odd 3-digit counting numbers that are less than 600. Okay, this tells us we don't have to worry about this kind of scenario like we did last time, but we do have to find so we have to find all 3 digits, and notice like last time we were limited to those 3. We're not limited this way. We can use any of the digits we want. Okay, so let's just write them down. We've got these to choose from, right? I'll just write the rest of them out here. It's all one line of ideas, but I just doubled them up. I just ran out of space. Okay, so how many of these? The most important thing when we're trying to build odd numbers is the ones place, right? That's where it has to be odd. 1, 2, 3, 4, 5 odd numbers will make this whole number odd. Make sense? Right? Okay. Then what about this digit? This digit could be anything, right? We can have any of the digits in there. It doesn't tell us about repetition. Let me double check. Repetition is permissible. Okay, so we can repeat the digits. That means we could put any of the 10 digits in there. Remember, there are 10 digits. 1 through 9 are 9 of them, and then 0 is the 10th digit. That can be such a mind bender sometimes. Some people, it takes a while to wrap their minds around that. But we have 10 choices here. Now, what about in the hundreds place? We can put anything. It doesn't affect what the number, the digit in the hundreds place does not affect whether it's odd or even. But we have to take this into mind. It has to be less than 600. So that means we can cross out 6, 7, 8, and 9. We also cross out 0 because 0, if we had a 0 here, then it wouldn't be a 3-digit number anymore, right? So that means our choices for this first box are 1, 2, 3, 4, and 5. That's 5 of them. It's head-bendy, isn't it? So remember, we multiply these together, and this would give us 250 ways that we can create odd 3-digit counting numbers that are less than 600. Ooh, it's crazy, right? Okay, let's try another one. One of my favorite problems of all time. My favorite problems of all time is coming up, and I'm excited. It's number 5, but we're on number 3. So, psych up. Okay. I have a different table today. I'll tell you why in just a minute. Okay, 5 math books and 4 English books sit on a shelf. How many permutations of the possible math books, how many permutations are possible if the math books must be kept together and the English books must be kept together? Okay, 5 math and 4 English. So let's draw a picture of that. And P.S., that's the answer to these, is you always draw a picture. Story of math life, right? Okay, so here are the English books. There are 4 of them, right? And then here are the math books. There are 5 of them. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, this is my dividing line between them. Okay, so we don't have to ask any questions about replacement because we know we're dealing with physical objects this time. And so obviously you can't use the same book twice, right? That's physically impossible. So we take a look at the math books. There are 5 of them. So in the first spot, we could put any one of them and fill in like so, right? This is just like what we've done in the past. Same for the English books. They have to be kept together, so it's 4, 3, 2, 1, right? Okay, so then we multiply all that out, and it is, this would be 5 times, there's a 10 and there's a 12. So this would be 120. And we would multiply it by, this is 624. And that gives us a total of 2880. So that's how many different ways. And it feels, the problem feels done until you stop and go, wait a minute, wait a minute, wait a minute. What if we took the English books and moved them to this side of the math books? We could reverse the subjects, right? It said we have to keep all the math togethers and we have to keep all the English togethers, but it didn't say that the math had to come first. Right? We could do it like this. And we could rearrange them all over again just like that. So we could do 4, 3, 2, 1 times 5, 4, 3, 2, 1. And that would give us 2,000 rather, 880 more ways. So we add these two. Sometimes students get confused by that. When we're drawing different scenarios, we don't multiply those together, we add them. We multiply within each scenario, and then we add together the different scenarios, and that gives us a grand total of 5,760 different ways that these two books, these two sets of books could be arranged, keeping them together within the subject matter, but mixing them up within. How many different 4-digit odd counting numbers can be formed if no repetition of digits is permitted? Okay, they have to be 4-digit, they have to be odd, and there's no repetition. All right, let's draw our boxes. 4 digits, so we don't have to worry about single digit, double digit, triple digit numbers like we did in that one problem. This is the fun of these, you guys, is you really have to just sort through each problem and use logic to figure it out. And I frankly think that's kind of fun. Okay, what are our choices? We have no limits on the digits, so let's write them all out again. It has to be odd. That tells us that we have to pay attention to the ones place. And we have 1, 2, 3, 4, 5 choices of what can go into there. All right. That's cool. There's no repetition. Let's turn our attention to this one next. This one, it's got to be 4 digits. So what that tells us is zeros out. We can't put 0 in this place. So that means we're down to 9 choices, but we've already used 1 here. So that means we're down to 8 choices. Okay? When we go to this box, you would think, well, now we're down to 7 choices, but 0's an option here, right? So we could use any of the 10 minus the 2 that we've used in these other 2 boxes. So this is also 8. And then that is 7. Does that make sense? That's tricky. You just have to be on your toes with these. When we multiply 8 times 8 times 7 times 5, we get 2,240 ways. All right. One more. Ready? Here we go. An elf, a gnome, a fairy, a pixie, and a leprechaun. Elf, gnome, fairy, pixie, and a leprechaun were to sit in a line. Now, before we go any further, my brain gets so distracted by this problem because I find myself thinking, what's the difference between an elf, a gnome, a fairy, a pixie, and a leprechaun? Do they look different? Some have wings. Like, I'm pretty sure a fairy has wings, right? But I don't think the others do. I'm not sure what pixies are. But this one would have wings. Are they all the same scale? Or would it be like trying to play with like Polly Pockets and a Barbie, you know, where they're just, and an American Girl doll, where they're not even the same scale. I try to visualize this and I get lost in the fun of trying to imagine what in the heck that would be. An elf and a gnome, that sounds sort of woodlandy, right? They should be in the forest. And a fairy, yeah, fairies are out there, but leprechauns? I don't know. Leprechauns could be in the forest too, but I'm not even sure what a pixie is. Garden gnomes, I go all Harry Potter here. It's just a fascinating image to imagine these 5 creatures. And the fun part is we get to imagine it because we have to figure out how these guys are going to sit together. And here's their drama. How many different ways can they sit if the elf and the gnome insist on sitting next to each other? Oh my gosh. So these two have to be together as they sit down. These guys can handle it wherever they sit, but these guys have to be together. So let's start visualizing what that might be. Here they are. Oh wait, I drew 1, 2, 3, 4, 5, 6. That's not a box, forget it. The elf and the gnome have to sit in the first 2 places. And then 1, 2, 3, 4, 5. They could switch, right? They'd still be together, but in this one the elf is first, and this one the gnome is first. If they're sitting here, then the remaining 3 would spread themselves out there, right? Okay, that makes sense. But then these guys could move down. Instead of sitting in the first 2 places, they could sit in positions 2 and 3. Right? Here they're sitting in positions 1 and 2. Now, let's put them in these 2 positions together. Does this make sense? We'll put the elf and then the gnome, and then we'll do the gnome and the elf, and then it would be 3, 2, 1, 3, 2, 1. They're so dramatic, aren't they? They're causing us such problems. Okay, now we'll try putting them, here they are in 2 and 3, let's put them in 3 and 4. Right, if you consider this 1, 2, 3, 4, 5. Here they go. So now elf and gnome are in position 3 and 4, taking turns as to who sits first. Everyone else is coping. And then the last scenario, we'll put them down here at the end, right? So here they're in 1 and 2. Here they're in 2 and 3. Here they're in positions 3 and 4. And now they're in positions 4 and 5. Elf, gnome, gnome, elf, 3, 3, 2, 1, 3, 2, 1. Within each row, we multiply, and then we add all the different scenarios together. So what we get is 6, right? Because it's 3, 2, 1. So there's 6 and 6 and 6 and 6. 1, 2, 3, 4, 5, 6, 7, 8. So that means when we add them all up, there are 48 ways that these lovely creatures, elf, gnome, fairy, pixie, leprechaun, can sit down, I'm imagining in a row on a moss-covered log with some butterflies flitting around and some old trees growing around them, gnarled, maybe a few little wildflowers. There are 48 ways they can arrange themselves on that log and still let the elf and the gnome sit together. Oh, I hope you've enjoyed this as much as I have, because I think that problem is hilarious. Okay, that is part A. Now, I didn't say there was part B, and I will tell you why. Part B, we're not going to do, and I'm going to explain to you exactly what it is and why not. It's our old friend, the two-variable analysis, and what John wants us to do is use a calculator to solve this problem. All right, what he is telling us is, okay, here is a graph that takes gold and relates it to silver. Some experiment that someone was doing. These are the data points that they found. Here they are graphed, the dots with the circles. That circle tells us that it's experimental data. That's what that notation suggests. And John wants us to first calculate by hand, the way we have been, what the equation of that line would be. He suggests we take the endpoints, which are right here at 120 and 1, being careful to read the graph properly. 120 and 1, and then this point is what? This would be 75 and 10. And he wants us to calculate what the equation of the line would be. That I want you to do, but that we've been doing, so that isn't hard. The second part of what he wants you to do is take a graphing calculator, which is the kind that has, I don't have mine handy, it's the kind that has the screen on it. And what he wants you to do is enter in the points. It's a straightforward process. You key up the right function, and then you enter all of these in. No, I think you enter them in pairs. You do the X and the Y, the X and the Y, the X and the Y, right? To create the pairs. And then you hit graph, and your calculator it'll give you a picture, but it'll also give you a read that looks like this. Y equals AX plus B. It will tell you, they use A for the slope instead of M. We use M. It gives you a slope value. It gives you a y-intercept. And it gives you what's called an R value, which is the correlation coefficient. So in other words, it tells you how well that experimental data fit the line. We're looking for a correlation value between, it's right here, it says, for experiments in social sciences, we'd like to have R values between -1 and -0.7, or between 0.7 and 1. So they can be negative or positive. For scientific data, we like it a little tighter. We like it between 0.9 and -1, or 0.9 and +1, right? It can be negative or positive, because that's just telling you whether the slope is positive or not. But for physical sciences, we like it to be tighter. For social sciences, we can get a little broader. So this one would be okay. This is a R value of -0.78. It tells us it's a negative slope. That's fine. But this tells us that it's okay if we were doing a social sciences experiment. But for pure science, that's a little loose. And we might consider refining our experiment or conducting a few more to make sure that the tolerances of the procedures are being observed precisely. But as scientists, we want to pay attention to the R value. I'm sorry, was I pointing at the wrong one? Oh, this is helpful. This shows us how the scientists took this information and turned it into equation, right? -0.21 is the slope. You got it right there. A equals -0.2075, rounded it to the hundredths place. And then here in the y-intercept place, 25.64, rounded that to 1 decimal place. Why you would round to 1 decimal place here and 2 decimal places there, I don't like that. I would say be consistent. Use the same number of decimal places. But for whatever reason, that's what they did. So here's where I'm at with this, you guys. It is very important and valuable that you are able to take data points, either graphed or in a table, and use them to create the equation of a line. We've been doing those problems. Punching the data into a calculator and getting the result is a distraction, in my opinion, at the high school level, because once we put calculators in our hands, we stop thinking about math and we just think about how to run the dang calculator. And at a point, we need to learn how to run the dang calculators. And that's what college level math is all about. But in high school, I don't want to distract your attention with a bunch of buttons if I can help it. With trig, we have to. But this is unhelpful. If you ever find yourself in a class where a teacher expects you to know how to do this, A, reach out to me, or B, Google it. It's easy, you guys. It's really easy. But here is what I'll also tell you. I have sent the vast majority of my students who completed this book have gone on to Edmonds Community College to take pre-calculus classes there at the college level, which is amazing. And the instructors there do not expect you to know how to operate a graphing calculator. They teach that from the fundamentals on. So don't worry about that. This is not going to set you back or anything. I think quite the opposite. Using a calculator in high school can be very distracting from learning the underlying concepts. So that's my speech. We're not going to do these problems that require you to use a graphing calculator. We will continue to do the problems that ask you to do it by hand, okay? To do the calculations yourself. So you don't have to worry about this. And what I want you to do when you come to a problem, like here's when 8 and 9 are like this, 8's easier to see. It says use a graphing calculator. The following data came from an experiment that involved lead and copper. Oh yeah, we see it. Okay, there's lead and copper. They tell us the abbreviations. Use a graphing calculator to find the equation of the line that best fits this data. So we take the lowest and the highest. We use those as our x and y, right? X is on the top, y is on the bottom. And we use the midpoint, not the midpoint, sorry, the slope formula, y2 minus y1 over x2 minus x1, and we calculate the slope, and then we pick any pair of the points, plug it in, and calculate the b, the value for b. So I want you to do these by hand and compare your work to what John gives us the answer, okay? All right, so nothing new. That's the end of lesson 45. I enjoyed it thoroughly, and I will see you next time.